All right, welcome back, everyone. Ready for another deep dive?
Definitely.
Today, we're tackling a pretty big chunk of the periodic table, the DNF blocks.
Right. Lots of interesting elements packed in there.
And looking at the material you guys sent in, it seems like you're really curious about what sets these elements apart.
Yeah, what makes them tick?
Exactly. And how their electron configurations, especially those DNF orbitals, play a role.
Really drive their behavior.
Yeah. So let's get started. First up, the D block elements, the heart of the periodic table, those metals in groups 3 through 12.
Right in the middle.
And it all starts with those d orbitals, right?
Yeah, those d orbitals getting filled up as you move across a period.
Instead of adding electrons to the outermost shell.
It's almost like working on the inner layers before the outer ones.
Yeah, it's a bit counterintuitive.
Definitely. But that's what makes them so interesting. Those d electrons, they're like the behind-the-scenes crew.
Oh, I like that.
They might not be in the spotlight, but they're the ones controlling the show.
The masterminds, pulling the strings.
Exactly. So to really understand their influence, we need to talk about electron configuration.
Okay, let's do it.
The general pattern for D block elements is N1DAO.
Okay, that's the basic blueprint.
Right, the foundation. But of course, there are exceptions.
Exceptions. I knew there had to be some.
There always are. And those exceptions are what make things interesting. Like, take chromium, for example.
Okay, chromium, what's it doing?
Instead of following the expected filling order, it prioritizes having a half-filled orbital.
So it's all about balance.
Exactly. Stability. And copper does something similar. It opts for a completely filled orbital.
So they're both going for those stable arrangements.
Exactly. Those full and half-filled orbitals are like those perfect puzzle pieces. They just fit.
They click right in.
Right. And this stability, this drive for a balanced electron configuration, that's a major player throughout the DNF block.
Okay, I'm starting to see that.
It's a key theme.
Now, what about zinc, cadmium, and mercury?
Good question.
They're in the D block, but they don't always act like the other transition metals.
Right. They're kind of the oddballs out.
A little different.
And it all comes back to their electron configurations. Their d orbitals are already full.
So they've already reached that stability.
Exactly. They're content. They don't need to participate in all the typical transition metal shenanigans.
They're just chilling, enjoying the party from a distance.
Right. Now let's move on to what makes transition metals, transition metal,
Those classic metal properties.
strong, shiny, fantastic conductors.
Yeah, those are the ones we picture when we think of metals.
Exactly. And those properties, they're all tied to how those d electrons participate in metallic bonding.
Oh, interesting.
Imagine it like a sea of electrons flowing freely between the metal atoms, holding them together.
So the d electrons are like the glue.
Precisely, the glue that binds everything together.
And the strength of that glue, that metallic bond, that's what influences melting points, right?
Exactly. And boiling points, too.
Okay, so how do those trends play out?
Well, as you move across a period, the melting points generally increase. They peak somewhere in the middle, and then they start to decrease again.
It's like climbing a mountain, reaching the peak, and then coming back down.
Perfect analogy. And as you add more electrons, those metallic bonds get stronger, requiring more energy to break.
So those elements in the middle, at the peak, they're the strongest.
Exactly. Their bonds are toughest to break.
Fascinating.
And this strength, this resistance to breaking apart, that's reflected in their enthalpies of atomization, too.
Remind me what enthalpy of atomization is again.
It's the energy needed to break all those bonds, to turn a solid metal into individual atoms.
Okay, right.
And for transition metals, those values are pretty high, especially for the elements near the middle where we see those half-filled orbitals.
So those half-filled orbitals, they really make a difference.
They do. It's all about stability.
Makes sense. And this reluctance to break apart, that's also why some metals are so resistant to reacting.
Right, like with acids, for example. Think about gold, notoriously unreactive.
Yeah, it pretty much stays the same.
Exactly. Those metallic bonds are so strong, it takes a lot of energy to persuade those atoms to separate and react.
They're like, nope, we're good here.
Right.
Yeah.
Content with their own company. Now, let's look at those atomization values across different periods.
Okay, what do we see there?
The metals in the second and third transition series, those further down the periodic table, they have even higher enthalpies of atomization.
So the heavier elements are even tougher to break apart.
Exactly. And this stronger bonding can lead to something pretty interesting, metal bonding.
Wait, metal atoms bonding with each other?
Yes. It's not as common as metal non-metal bonding, but it does happen.
Wow, I never thought about that.
Right. It's especially prevalent in those heavier transition metals, where those metallic bonds are so strong they can even bond with each other.
That's pretty cool.
It is. It shows how much more there is to metallic bonding than we might initially think.
Definitely. Okay, so we've talked about those attractions between metal atoms, but what about the size of those atoms?
Good point.
I know atomic size generally decreases across a period, but does that hold true for the D block?
Well, it's a bit more nuanced with transition metals. There's a general decrease, but the changes are pretty subtle.
Okay, subtle, not dramatic.
Right. But when we compare sizes between periods, that's where things get interesting.
Okay, I'm intrigued. What happens?
Well, as you go down a group, you're adding another electron shell, so you'd expect the atoms to get bigger, right?
Yeah, more shells, more space.
Right. Oh, but when we get to the third transition series, those 5D elements, they don't follow the script.
Uh-oh, rule breakers.
They are. Their radii are almost the same as those in the second series.
So they're smaller than expected.
Exactly. It's like they hit a size limit. And the culprit behind this is the lanthanide contraction.
Ooh, that sounds serious. Lanthanide contraction? What is that?
It's all about the F block elements, those lanthanides hiding at the bottom of the periodic table.
Okay, the lanthanides are involved.
They are. See, before we get to those 5D elements, we have to fill up the 4f orbitals in the lanthanides.
It's like a detour on the electron-filling highway.
Exactly. And those 4f electrons, they're not very good at shielding each other from the increasing nuclear charge.
So the atomic size decreases across the lanthanide series.
Precisely. So by the time we reach the 5D elements, the atoms have already shrunk significantly.
Thanks to the lanthanides.
Exactly. And this has some interesting consequences, like zirconium from the second series and hafnium from the third series. They end up with almost identical radii and very similar properties.
Even though they're in different periods.
Right. It's a great example of how different parts of the periodic table can be connected in unexpected ways.
Wow, the lanthanides are really shaking things up.
They are. You're playing a long game. Now let's talk about atomic size and density.
Okay, density, how tightly packed matter is.
Right. And as you move across a transition metal series, you're adding more protons and neutrons to the nucleus, increasing the mass.
Some more stuff.
Right. But at the same time, the atomic size is slightly decreasing.
So it's like squeezing more stuff into a smaller box.
Exactly. Higher density. And that's what we see in the D block. Take the third series, from titanium to copper, you see a significant jump in density.
Okay, that makes sense. More mass, smaller space, denser material.
Precisely. Now, we can't talk about electron configuration without discussing ionization enthalpies.
Okay, ionization enthalpy, that's the energy needed to remove an electron from an atom, right?
Exactly. It's like measuring how strongly an atom is holding onto its electrons.
Got it. So as we move across a series of transition metals, does ionization enthalpy increase?
Generally, yes. The number of protons in the nucleus is increasing, so those electrons feel a stronger pull.
Okay, stronger pull, harder to remove those electrons.
Right. But, of course, there are irregularities.
I knew it.
There always are. If you look at the first ionization enthalpies of the third series, there's a slight dip at manganese and iron.
Okay, so they're a bit easier to ionize.
Right. And it comes back to those third electrons in those inner orbitals. As the nuclear charge increases, those third electrons get better at shielding the outermost 4s electrons.
So those 4s electrons are feeling less of that nuclear pull.
Exactly. And that's why we see that slight dip.
Okay, so shielding is playing a role here.
Definitely. But when we look at the second and third ionization enthalpies, the trend is more pronounced.
So once you start removing those inner electrons, things get harder.
Exactly. Less shielding.
But I'm guessing there are more exceptions.
You bet. The second ionization enthalpy for manganese is lower than expected, and the same happens for iron with the third ionization enthalpy.
Okay, so what's going on there?
Well, those exceptions, they tell us a lot about stable electron configurations.
Stability. That word keeps popping up.
It's crucial. When we remove an electron from MNA to form MNAO, we end up with a door configuration.
That half-filled orbital arrangement.
Exactly, and that's particularly stable.
Makes sense. And the same thing applies to iron, right?
Right. Theo, losing an electron to form Theo, also gives you that DOI configuration.
So those exceptions are like clues pointing us towards stable arrangements.
Exactly, little hints from the elements themselves. And those ionization enthalpies, they also give us clues about another key characteristic of transition metals, their variable oxidation states.
Ah, yes. Their ability to exist in multiple oxidation states.
Like iron being both Feo and Feo.
Right. It's almost like they have multiple personalities.
It is, and it all comes down to those d electrons being relatively easy to lose or share. If you look at the first row of transition metals, you see a range of possible oxidation states.
So some have a narrow range, others have a wider range.
Right, and the elements with the widest range tend to be in the middle of the series.
Okay, so there's a pattern there?
There is. The elements at the beginning, they don't have many d electrons to lose or share, so their options are limited.
So scandium usually sticks with +3.
Right. But as you move towards the middle, you have more d electrons to play with, more possibilities.
More options, more flexibility.
Exactly. But then as you reach the ends, like with zinc, the d orbitals are already full.
So they're happy as they are.
Exactly. They don't want to lose or share those electrons.
Content with their full D shell.
Precisely. And these variable oxidation states, this flexibility, that's what makes transition metals so important in things like catalysis.
Right. They can change roles, facilitate reactions.
Exactly. And those d electrons can also absorb light, creating those beautiful colors we see in some compounds.
Ah, yes, those vibrant colors.
Right. It's all connected to those d electrons.
This is making me realize how much those D electrons are in charge.
They are. They're pulling the strings.
Okay, let's shift gears and talk about standard electrode potentials.
All right.
I know it has to do with how easily a metal loses electrons to form positive ions.
Exactly. How easily they get oxidized.
So a more negative standard electrode potential means the metal is more likely to give up electrons.
You got it. More reactive.
Okay, that makes sense. So if we look at the MNF's standard electrode potentials for the first row of transition metals, is there a trend?
Yes, there is. You generally see less negative values as you move across the series.
Meaning they're less willing to lose those 2 electrons.
Precisely. And it's related to the increasing sum of the first and second ionization enthalpies.
Right, it takes more energy to remove those electrons.
Exactly. But, as always, we have some exceptions.
Of course we do. Which one's this time?
Manganese, nickel, and zinc.
Okay, so they have more negative values than we'd expect.
Right. Manganese and zinc, it's all about those stable electron configurations again.
Monyu with that half-filled door configuration.
Exactly. And Zn with its full Dua configuration.
So they're happy and stable, not eager to lose electrons.
They're content as they are. But nickel, it's a bit different.
Okay, what's going on in nickel?
It has a high negative enthalpy of hydration.
Enthalpy of hydration, that's the energy released when ions are surrounded by water molecules, right?
Exactly. And nickel releases a lot of energy during this process.
So even though its ionization enthalpies are high, that hydration energy makes it more favorable to form Ni ions.
Precisely. That interaction with water is a major factor.
Okay, so it's a balancing act.
It is. Ionization enthalpies versus hydration enthalpies.
And the winner determines the reactivity.
Exactly. Now, what about those Ullmann standard electrode potentials?
Okay, so how easily a metal loses an electron when it's already in a +2 state?
Right. We see some interesting variations there, highlighting the stability of different oxidation states.
Interesting. Give me some examples.
Okay, so scandium has a very low Ullmann standard electrode potential, showing how stable it's SCA as.
Why is that?
It has a noble gas configuration.
Ah, that full outer shell.
Right. Complete stability. But then we have zinc with the highest value for this potential.
Why is zinc so high?
Because removing an electron from Zn would disrupt its stable Dewar configuration.
So it really doesn't want to lose that electron.
Exactly. And manganese also has a relatively high value, showing how stable MRO is with its half-filled Dew configuration.
Half-filled shell, stable again.
It keeps coming back. And iron, it has a lower value because FeO, with that Dew configuration, is more stable.
Makes sense. And vanadium.
Vanadium has a low value because its V ion has a half-filled Euro level.
That's a specific type of d orbital, right?
Yes, it is. We can dive into those details another time, but for now, just know that a half-filled Euro level is also stable.
Okay, noted. So all these variations tell us how happy or unhappy different metals are in different oxidation states.
Precisely. And it all comes back to those d electrons.
Those d electrons, they really are calling the shots.
They are. They're the key players in transition metal chemistry. Now, we've talked a lot about oxidation states, but what about how high those oxidation states can go?
Yeah, that's a good question. Some elements seem to stick to lower states, while others go really high.
Right, and it often depends on what the transition metal is bonding with.
Okay, so what are the important factors?
Electronegativity, for one.
Right, that's how strongly an atom attracts electrons in a bond.
Exactly. And some elements are really good at pulling electron density away from transition metals, allowing them to reach those higher oxidation states.
So if a metal is bonded to a very electronegative element, it basically gives up more control over its electrons.
Precisely. And that pushes it to a higher oxidation state.
Interesting. So which elements are the best at this?
Fluorine and oxygen are the champions.
Fluorine, the most electronegative element, and oxygen, the master of double bonds.
Exactly. They're incredibly efficient at pulling electron density away.
So those high oxidation states, we should expect to see them when metals are bonded to either fluorine or oxygen?
Absolutely. Take a look at the halides and oxides of the third series. You'll see those high oxidation states in compounds like TiCSu, VFU, and even CRFE.
Wow, +6 for chromium and CRFU. That's impressive.
It is. And while we don't see a simple MnO halide, the compound MnOS does exist, showing how oxygen can sometimes stabilize those higher states.
So oxygen can be more effective than fluorine in some cases.
Right, and it comes down to those multiple bonds that oxygen can form.
Ah, those multiple bonds giving oxygen extra pulling power.
Exactly, like extra ropes in a tug-of-war.
So are there any other ways to stabilize those high oxidation states?
Yes. We also see them in oxycations.
Oxycations, remind me what those are.
Those are positively charged ions that contain both a metal and oxygen.
Oh, right. So like VOU, where vanadium has a +5 oxidation state.
Exactly. And we also see VO and TO in TO.
So oxygen is playing a key role even within those positive ions.
It is. And in many cases, oxygen's ability to stabilize those high states is even greater than fluorine's.
Wow, oxygen really is a powerful force.
It is. And again, it's those multiple bonds. Think about MnEuro, for example.
Okay, what's special about that one?
Well, in this covalent oxide, each manganese is surrounded by oxygen atoms, including a MnONN bridge, and each manganese forms multiple bonds to those oxygens, reaching that +7 oxidation state.
So those multiple bonds are giving manganese the boost it needs.
Exactly. And these high oxidation states, they play a big role in the reactivity and properties of these compounds.
Okay, that makes sense. Now, what about magnetic properties? I know transition metals can be a bit unpredictable in that area.
Right. Magnetic properties, how a substance responds to a magnetic field.
So it's like each element has its own magnetic personality.
Exactly. And there are two main types of behavior, diamagnetism and paramagnetism.
Okay, remind me of the difference.
Diamagnetic substances are repelled by a magnetic field, while paramagnetic substances are attracted to it.
So it's like how they react to a magnet, one pushes away, the other stick.
Exactly. And guess what? Many transition metal ions are paramagnetic.
Really? Why is that?
It's all about those unpaired electrons in the d orbitals.
Ah, those unpaired electrons. They always seem to be at the heart of things.
They are. Each unpaired electron acts like a tiny magnet spinning around, creating a magnetic moment.
So each unpaired electron has its own little magnetic field.
Precisely. And when you have multiple unpaired electrons, those magnetic moments add up, making the ion paramagnetic.
Okay, so more unpaired electrons, stronger the magnetism.
Exactly. Now, for the first series of transition metals, the magnetic moment is mainly determined by the number of unpaired electrons.
So we can actually calculate it based on that.
We can. There's a formula called the spin-only formula.
So if we know how many unpaired electrons an ion has, we can figure out how magnetic it is.
Precisely. And that calculated magnetic moment can give us clues about the electron configuration, too.
So it's like a magnetic fingerprint.
It is a window into the electronic structure.
Amazing how much information is packed into those properties.
It is. And it highlights the connection between electron configuration, magnetism, and behavior.
Definitely. Okay, so we've covered magnetism. Now let's talk about how transition metals actually react.
All right, reactivity.
They're not as straightforward as those alkali metals that go crazy with water.
Right, definitely not. Their reactivity varies quite a bit. Many are electropositive enough to dissolve in acids.
So they give up electrons easily.
Right, forming those positive ions.
So we're talking about those classic metal-acid reactions,
Yeah.
right?
Exactly. But then you have the noble metals, like gold and platinum.
They're pretty much unaffected by single acids.
Right. They hold on to those electrons tightly.
They're like not interested.
Exactly. Now, if we focus on the first series, excluding copper, they're generally more reactive. They can be oxidized by even 1 met.
Okay, so they have the potential to be reactive.
They do. But the rate of reaction can be surprisingly slow.
So they're not always as reactive as we might think.
Right. Titanium and vanadium, for example, they're notoriously slow to react with dilute acids at room temperature.
Interesting. So they're not always quick to jump into reactions.
Right. It's all about kinetics, the speed of the reaction.
Makes sense. So looking at those standard electropotentials again, is there a trend in the tendency to form those divalent cations?
Yes, there is a decreasing tendency as we move across the series.
So less inclined to lose those two electrons.
Precisely. And again, it's tied to those increasing ionization enthalpies.
Right, harder to remove those electrons.
Exactly. But you guessed it, there are exceptions.
I'm starting to expect them now. Which ones are bucking the trend this time?
Manganese, nickel, and zinc.
Those three again.
They like to keep things interesting. And it's a great example of how multiple factors can influence reactivity.
Right, not just one thing.
Exactly. So manganese and zinc, they have those stable electron configurations.
Makes them less willing to lose electrons.
Right. But their hydration enthalpies come into play.
So that energy released when they interact with water, that can encourage them to react.
Precisely. It's a delicate balance.
A tug of war between stability and the energy from hydration.
Exactly. And the winner determines the overall reactivity.
This is really showing me how complex reactivity could be.
It is. It's not always a simple yes or no.
Okay, so we've talked about reactions with acids, but what about reactions with nonmetals, like oxygen?
Ah, those are important ones.
Yeah, those metal oxides are everywhere.
They are. They're the basis of pigments, batteries, so many things.
Okay, so we're talking about compounds like iron oxide or rust?
Exactly. And titanium dioxide, which is used in sunscreen.
Right. So how are those oxides formed?
Well, for the first series of transition metals, it's usually by heating the metals in the presence of oxygen.
So a direct reaction.
Right. A fiery combination. And those oxides, they exhibit a fascinating range of properties.
Okay, what kind of properties?
Well, they can range from basic to acidic.
Basic oxides react with acids, acidic oxides react with bases, right?
Exactly. And some can even be amphoteric.
Amphoteric, meaning they can react with both acids and bases.
Exactly. They're versatile.
Okay, so what influences whether an oxide is basic, acidic, or amphoteric?
It all comes down to the oxidation state of the metal.
So the higher the oxidation state, the more acidic the oxide.
Precisely. It's a great example of how electron configuration influences properties.
Okay, I'm ready for some specific examples. What are some key transition metal oxides?
Well, let's start with manganese. It forms a variety of oxides ranging from MnO to Mn-urose.
Wow, that's quite a range. So MnO would be the most basic, and MnO is the most acidic.
Exactly. M-arrow is so acidic, it reacts with water to form permanganic acid.
Permanganic acid, that's a powerful oxidizing agent, right?
It is. So manganese really shows how those oxidation states can change an oxide's character.
Okay, what about chromium?
Chromium forms CaRO and CrO.
And CR is a basic, while CrO is amphoteric.
Right. It can react with both acids and bases.
Versatile chromium.
Exactly. And then we have vanadium.
Okay, what does vanadium do?
It forms VO-auros, VO, and VO.
Another wide range of oxidation states.
Right. And VO is so acidic, it's used as a catalyst in the production of sulfuric acid.
Wow, so these oxides are involved in some big industrial processes.
They are. They're essential.
Okay, so we've covered a lot of ground with the D block elements.
We have. It's a fascinating group.
It is. Now I'm ready to move on to the F block.
All right. The lanthanides and actinides.
Those elements at the bottom of the periodic table, often forgotten.
Right. But they're incredibly important.
They are. So what makes them unique? What sets them apart from the D block elements?
Well, it all comes down to those f orbitals.
Those F orbitals buried deep within the atom.
Exactly. And fit of those orbitals, that's what defines the F block elements.
Okay, so let's start with the lanthanides. What makes them stand out?
Well, one of the most striking things about the lanthanides is their similarity to each other.
They're like a close-knit family.
Exactly. And they all have a strong preference for the +3 oxidation state.
So they're pretty consistent in their behavior.
They are. And that similarity comes from the fact that those 4f electrons are buried so deep.
Shielded from the outside world?
Precisely. They're less involved in bonding, so there's less variation in their chemical behavior.
Okay, but I'm sure there are some subtle differences.
Of course. And one of the most significant trends is the lanthanide contraction.
Right, that shrinking atomic size as we move across the series.
Exactly. And it has a big impact on their properties.
Yeah.
Yeah, it's like they're breaking the rules of atomic size.
Right. Usually atoms get bigger as you go down a group.
More shells, more space.
But the lanthanides, they're shrinking.
They are. And it all goes back to those 4f electrons.
Those 4f electrons always causing trouble.
Well, they're not very good at shielding each other from that increasing nuclear charge.
So as you add more 4f electrons, they don't protect each other well from the nucleus.
Exactly. So each added electron feels a stronger pull towards the nucleus.
So the whole electron cloud gets pulled in tighter.
Precisely. The atom shrinks.
Wow, so the lanthanide contraction is really a battle between those 4f electrons in the nucleus.
It is. And the nucleus is winning.
So how does this shrinking size affect the lanthanide's reactivity,
Well, as the atoms get smaller, the outermost electrons are held more tightly.
making them less available for bonding?
Exactly. So, in general, the lanthanides become less reactive as you move across the series.
Okay, that makes sense.
But of course, there are exceptions.
Exceptions, I was waiting for those.
There always are. Europium and ytterbium, for example, they exhibit the +2 oxidation state more readily.
Ah, so they prefer a lower oxidation state.
Right, and it's all about stability again.
Those stable electron configurations.
Exactly. Europium, when it forms UO, achieves a half-filled 4f subshell.
And europium, when it forms YBO, gets a completely filled 4f subshell.
Precisely. They're willing to sacrifice that typical +3 state to achieve those stable configurations.
Fascinating how those electron arrangements drive their behavior.
They do. They're the underlying force behind so much of chemistry. So lanthanide contraction affects reactivity, but what else?
Yeah, what other properties does it influence?
It also affects their ionization enthalpies.
Right, the energy required to remove an electron,
Exactly. And as those atoms get smaller, those outer electrons are held tighter.
making it harder to remove them.
Precisely. So you'd expect ionization enthalpies to increase across the series.
Okay, makes sense.
But guess what? There are exceptions.
More exceptions. I should have known.
Always exceptions. Lanthanum, gadolinium, and lutetium, they have lower ionization enthalpies than expected.
Okay, so they're easier to ionize.
Right. And again, it's about those special electron configurations.
Stable arrangements, I
You
bet.
got it. Lanthanum, when it forms Loth, ends up with an empty 4f subshell.
Okay, empty subshell.
Gadolinium, in its Gido form, has a half-filled 4f subshell.
Half-filled, stable.
And lutetium, when it forms Lu, achieves a completely filled 4 subshell.
Completely filled, super stable.
Exactly. So even though those outer electrons are held tighter due to the contraction, these elements are willing to let go to reach those stable configurations.
It's like they're saying, I know I'm supposed to hold on tight, but stability is more important.
Precisely. It shows the power of those electron arrangements.
Definitely. Okay, so we've talked about the microscopic world of electron configurations and ionization energies. Now let's zoom out and talk about what the lanthanides actually look like.
Right? Their physical appearance.
Yeah, what do we see when we look at a lanthanide?
Well, they're typically silvery white, soft solids.
Classic metal look.
Right. But they tarnish quickly in air, reacting with oxygen.
So they're not very resistant to the elements.
Not particularly. They're more reactive than the transition metals, but there's one exception to their softness: samarium.
Samarium. What's special about it?
It's actually quite hard, almost as hard as steel.
Wow, samarium, the tough one.
It is. And speaking of variations, their melting points also span a range.
Okay, so some melt easier, some harder.
Right. But samarium, again, is an outlier.
Of course it is.
It melts at a much higher temperature.
Samarium, the rule breaker.
It definitely likes to stand out. But apart from those
well-
exceptions, the lanthanides generally exhibit similar properties.
Okay, so back to those family resemblances.
Right. They have typical metallic structures. They're good conductors of heat and electricity. Their densities also change smoothly across the series, except for, you guessed it, europium and ytterbium.
Those two again. And sometimes samarium and thulium join the party.
Right. Those 4f electrons can have subtle effects.
Okay, now let's add some color to this discussion.
Literally.
Literally. Many lanthanide ions are colored.
They are, both in solid compounds and in solutions.
So we're talking pinks, greens, blues.
Those and more. It's all due to those 4f electrons.
Those 4f electrons, always up to something.
They are. When light interacts with a lanthanide ion, those 4f electrons can absorb certain wavelengths.
And that causes the solution to appear a certain color.
Exactly. The complementary color of the light absorbed.
So, like, if they absorb blue light, the solution might appear orange.
Precisely. But the colors can be subtle, often pale shades,
Why is that?
because the absorption bands are relatively narrow.
So they only absorb a small range of wavelengths.
Exactly. They're picky eaters when it comes to light.
I like that analogy. So they only absorb a little bit of the visible spectrum, resulting in those pale colors.
Right. Now, there are two exceptions to this colorful trend: LaO and LuO.
LaHo and Luo. back to their colorless ways.
Right. And it's all about their stable electron configurations.
Of course it is.
LuO has an empty 4-half subshell, and LuO has a completely filled one.
So no partially filled orbitals to absorb light.
Exactly. They reflect all the colors, appearing colorless.
Okay, makes sense. Now, besides color, those unpaired 4 electrons also contribute to paramagnetism.
Right. Their attraction to a magnetic field.
And all lanthanide ions, except those with empty or full 4 subshells, are paramagnetic.
They are. Those unpaired electrons act like tiny magnets.
So we can use that to study their electronic structure.
We can. It's another tool for understanding their behavior.
Okay, so we've covered electron configuration, size trends, reactivity, color, magnetism. What's next?
Let's talk about how those lanthanides react with other elements, how they form compounds.
All right, compound formation time. What kind of reactions are we talking about?
Well, in terms of reactivity, the earlier lanthanides, those closer to lanthanum, are more reactive.
Okay, so like calcium.
Exactly. But as you move across the series, they become more like aluminum.
So they shift their reactivity personality.
Right. And one way to measure their reactivity is through their standard electrode potentials.
Standard electrode potentials, those tell us how easily they gain or lose electrons.
Exactly. And we look at the potential for the reaction where the LNU ion gains 3 electrons to form the solid metal.
Okay, so how easily they go from ion to metal.
Right. And for most lanthanides, these values fall in a pretty narrow range.
Okay, so they're pretty consistent.
They are. But of course, there's an exception.
There's always an exception. Which one this time?
Europium.
Europium. Always breaking the mold.
It has a less negative standard electrode potential, meaning it's less likely to form the solid metal.
So it prefers to stay as an ion?
It does, and it's because of its tendency to form UO.
That stable +2 state again.
Right. Now let's move on to some specific reaction.
Okay, I'm ready to see the lanthanides in action.
They react readily with hydrogen gas when heated, forming hydrides.
Lanthanide hydrides.
Right. They also react with carbon, forming carbides.
Carbide compounds.
Exactly. And they react with acids, releasing hydrogen gas and forming salts.
Classic acid-metal reaction.
Right. And they also have a strong affinity for halogens.
Forming halide.
Precisely. So they're quite versatile, reacting with a variety of elements.
Okay, so they can form a whole range of compounds.
They can. Now, let's talk about how these properties translate into applications.
Okay, I'm curious, how are we using these lanthanides in the real world?
Well, one of their major uses is in alloys.
Alloys, mixtures of metals.
Exactly. A particularly important one is mish metal.
Mish metal, that's a fun name.
It is. It's primarily a mixture of lanthanide metals with a little bit of iron and some other trace elements.
Okay, so a blend of lanthanides.
Right, and a lot of it is used in magnesium-based alloys.
Magnesium alloys, what are those used for?
They're used to make things like bullets, shells, and lighter flints.
Wow, so those lanthanides are ending up in some pretty interesting things.
They are, and their oxides are also important.
Okay, what about the oxides?
Mixed lanthanide oxides are used as catalysts in petroleum cracking.
Petroleum cracking, that's a big deal.
It is. It's breaking down large hydrocarbon molecules into smaller, more useful ones.
So they're helping to refine the fuels we use.
Exactly. And some individual lanthanide oxides, like those of europium and terbium, are used in displays.
Displays, like TV screens.
Exactly. They're used as phosphors, creating those bright, vibrant colors.
Wow. So the lanthanides are really playing a big role behind the scenes.
They are. They're essential for many technologies we use every day.
Okay, so from alloys to catalysts to displays, the lanthanides are proving their worth.
They are. Now, are you ready to move on to the actinides?
Absolutely. The heavier, more radioactive members of the FEFLOC.
Right. The actinides, they're a fascinating bunch, but their radioactivity can make them a bit challenging to study.
Okay, what are the challenges?
Well, the earlier actinides, like thorium and uranium, they have relatively long half-lives.
So they stick around for a while.
They do. But as you move towards the later actinides, those half-lives get incredibly short.
We're talking minutes, hours.
Sometimes even less. They decay very quickly.
So those later actinides are like fleeting glimpses, hard to catch.
They are. And because of that radioactivity, many of them can only be produced and studied in very small amounts.
So we're talking a few atoms at a time.
Sometimes, yes. It's incredible what scientists can do with such limited samples.
It is. Now let's talk about electron configuration.
Right.
Do they follow a similar pattern to the lanthanides?
They do. Generally, they have 7 subvectional electrons and then a variable number of electrons in their 5 and 6 orbitals.
So they're filling those inner 4 orbitals like the lanthanide.
Exactly. But, you guessed it, there are exceptions.
I'm starting to think those exceptions are just the rule in the F block.
They're definitely common. Thorium, for example, it doesn't have any 5F electrons in its ground state.
It's like it's skipping that step.
It is. It prefers to keep its 6-bit orbitals filled.
Okay, so thorium is doing its own thing.
It is. But from protactinium onwards, those 5F orbitals start to get filled.
So they join the party eventually.
They do. But there are still variations. Americium and curium, for example, their configurations highlight the stability of a half-filled 5F subshell.
That half-filled stability, it's everywhere.
It is. It's a fundamental principle in electron configuration.
Okay, so the actinides are filling those psi phi orbitals, but are there any other key differences compared to the 4F orbitals in the lanthanides?
Yes, those 5 orbitals are a bit more exposed.
Exposed. What does that mean?
It means they can interact more strongly with neighboring atoms.
So they're more involved in bonding.
Exactly. And that leads to a wider range of oxidation states and more diverse chemical behavior compared to the lanthanides.
So the actinides are a bit more flexible.
They are more unpredictable in a way.
Okay, I'm ready to dive into those oxidation states. What kind of range are we talking about?
Well, while the +3 state is common for both lanthanides and actinides, the actinides have a much wider range.
So they're not as limited to that +3 state.
Right. For the earlier actinides, we see a trend of increasing maximum oxidation states.
So it goes up and then down.
Exactly. Thorium is typically +4, protactinium can reach +5, uranium goes up to +6, and neptunium can even get to +7.
Wow, +7, that's impressive.
It is. But then, as you move towards the later actinides, those maximum states start to decrease again.
Okay, so it's a bit of a roller coaster ride.
It is. It reflects the complex interplay of those 5, 6-pence, and 7s electrons.
So it's not always easy to predict what oxidation state an actinide will prefer.
Exactly. It depends on the reaction conditions, the other elements involved.
Context matters.
It does. Now let's talk about their physical characteristics.
Okay, what do they look like?
They're generally silvery in appearance, like the lanthanides.
So that classic metallic shine.
Right. But their structures are a bit more diverse.
Diverse, what does that mean?
It means they don't all pack together in the same way.
So they have different crystal structures.
Exactly. And those variations are linked to irregularities in their metallic radii.
Irregularities.
Yeah.
I thought we saw a steady decrease in size across the lanthanide series.
We did. But with the actinides, the contraction isn't as smooth.
So there are more bumps in the road.
Right. Those size fluctuations affect how they pack together.
Makes sense. Different sized atoms will arrange themselves differently.
Exactly. And this structural diversity is just one way the actinides stand out from the lanthanides.
Okay, so they're more complex structurally.
They are. Now, what about reactivity?
Okay, are the actinides as reactive as the lanthanides?
They're even more reactive, especially when they're finely divided.
Finely divided.
Right. Lots of surface area for reactions.
So those tiny particles are ready to go?
They are. For example, if you expose finely divided actinides to boiling water, you get a pretty vigorous reaction.
Boiling water. Wow, they're not messing around.
They're not. They form oxides and hydrides.
So even water can't resist their reactivity.
Right. And they react with most nonmetals at fairly low temperatures.
So they're eager to bond.
They are. Now, reactions with acids are a bit more nuanced.
Okay, what happens there?
Hydrochloric acid can attack most actinide metals.
Okay, so they're susceptible to hydrochloric acid.
They are. But nitric acid is a bit trickier.
Trickier. How so?
Many actinides form a protective oxide layer when exposed to nitric acid.
So they create their own shield.
Exactly. It prevents further reaction.
Clever actinides. And what about alkalis like sodium hydroxide?
They generally have little effect on actinides.
So they can handle those strong basic conditions.
They can. They're resistant.
Okay, so their reactivity varies depending on what they're reacting with.
Right. It's a complex picture.
Now, what about their magnetic behavior?
Another fascinating aspect. The magnetic properties of the actinides are more complex than those of the lanthanides.
More complex. How so?
Well, both groups can be paramagnetic.
Right, because of those unpaired electrons.
Exactly. But the details of their behavior can be quite different.
Interesting. So even though they both have unpaired Abloff electrons, they don't always act the same way magnetically.
Right. And one way we study this is by measuring their magnetic susceptibility.
Magnetic susceptibility, that tells us how strongly they're magnetized, right?
Precisely. And while the general trend across the actinide series is similar to the lanthanides, the actual values for actinides tend to be higher.
So they're more magnetic.
They are, and that suggests those 5 electrons are playing a more active role.
Those exposed 5 orbitals making a difference again.
They are. They're influencing not just reactivity and oxidation states, but magnetism too.
Okay, so a lot going on with those 5 electrons. What about ionization enthalpies?
Good question. The data for actinides is a bit less complete because those heavier elements are harder to study.
Right, those short half-lives.
Exactly. But what we do know is that the ionization enthalpies for the early actinides seem to be lower than those of the corresponding lanthanides.
So it's easier to remove electrons from those early actinides.
Precisely. And it all comes back to those 5 l orbitals.
Okay, how so?
Well, remember, those 5 orbitals are more exposed.
Right, they don't penetrate as deeply into the core,
Exactly. So they're further from the nucleus.
meaning they're not held as tightly,
Precisely. They're more effectively shielded from the positive charge of the nucleus.
so they're easier to remove, lower ionization enthalpies.
Exactly. And this is another factor contributing to their higher reactivity.
It's all connected. Those exposed 5 orbitals lead to lower ionization and enthalpies, which lead to greater reactivity.
It's a beautiful example of how those seemingly small differences in electron configuration can have big consequences.
Definitely. Okay, so we've explored both the lanthanides and actinides in detail.
We have 2 fascinating groups.
They are. So how do they compare? What are the key similarities and differences?
Well, one of the biggest differences is their range of oxidation states.
Right, the lanthanides mostly stick to +3,
They do. They're more predictable.
while the actinides, they're all over the place.
They are. They exhibit a much wider range of oxidation states.
So they're more versatile.
Exactly. And that comes from those 5 orbitals being more available for bonding.
Right, those exposed 5 electrons.
Precisely. And that also leads to greater structural diversity in the actinide metals.
So the lanthanides are more uniform in their structures, while the actinides are more adaptable.
A perfect way to put it. And in terms of reactivity, the actinides are generally more reactive.
Especially those finely divided ones.
Exactly. They're ready to react with almost anything.
And those lower ionization enthalpies are helping them along?
They are, making those electrons easier to remove.
Okay, so those are some key differences. What about similarities?
While both groups exhibit that decrease in atomic and ionic radii across the series.
Right, that lanthanide contraction we talked about.
Exactly. And the actinides have a similar, though less regular, contraction.
So they're both getting smaller as you move across the series.
They are, and that affects their reactivity, their ionization enthalpies, their ability to form complexes.
So even though they have different trends in oxidation states and reactivity, they share that fundamental shrinking size.
They do. And another similarity is that they both tend to form predominantly ionic compounds.
So those electrostatic attractions between oppositely charged ions.
Precisely. That's a key driving force in their chemistry.
Okay, so even though they have their differences, they share some fundamental characteristics because they're both in the F block.
Exactly. They're both shaped by those F orbitals.
This has been an incredible journey through the D and F block elements.
It has. So much to explore.
I feel like I've gained a whole new perspective on the periodic table.
It's amazing how much depth there is to those elements.
It is. Now, for a final thought-provoking question for our listeners.
Okay, I like a good challenge. What are you thinking?
Well, we talked about those vibrant colors and transition metal compounds.
Right, those d electrons absorbing light.
Exactly.
Yeah.
But what if we could use that light absorption for something more than just pretty colors?
Ooh, I like where you're going with this.
What if we could harness that to develop new types of solar cells?
Solar cells. That's a great idea.
Or maybe create materials that change color in response to certain stimuli.
Like sensors.
Exactly. Sensors for pollution, medical conditions, all sorts of things.
That's brilliant. So by understanding those d electrons and how they interact with light, we could create some amazing new technologies.
Exactly. It's all about using that fundamental knowledge to solve real-world problems.
And that's what makes chemistry so exciting. The possibilities are endless.
Wow. What a journey through the D and F block. It's incredible how much is packed into those seemingly small sections of the periodic table.
I know, right? They're like hidden treasure chests full of chemical wonders.
They really are.
Yeah.
I feel like I've gone from barely knowing they existed to understanding their personalities and their importance.
It's been fun exploring them with you. So, ready for a final recap?
Absolutely. Hit me with those key takeaways.
All right. First off, The D block elements, those transition metals, they're all about diversity.
Right, from super reactive to super stable.
Exactly. And those partially filled orbitals, they're the key.
They're driving all those unique properties, those variable oxidation states, those colorful compounds, their catalytic abilities, even their magnetic behavior.
It all comes back to those D electrons.
It's like they have this special set of tools that allows them to do all these amazing things.
They do, and that's why understanding those D electrons is so crucial for understanding their chemistry.
And their role in all sorts of applications.
Absolutely. We can't forget how important the D block elements are in our everyday lives.
Right, they're everywhere. From buildings and bridges to cars and computers.
They're the backbone of modern technology.
And then we have the F block elements, the lanthanides and actinides.
Those often forgotten elements at the bottom of the periodic table.
But they're making their mark, too.
Absolutely. They're essential in high-tech displays, powerful magnets, even nuclear energy and medicine.
Their chemistry might be a bit more complex and challenging to study.
It is. But it's also incredibly rewarding.
It is. It really pushes the boundaries of what we know about periodicity and how those electrons influence behavior.
It shows us just how intricate and fascinating the world of chemistry can be.
It really does. This deep dive has been an incredible learning experience.
I'm glad you enjoyed it. It's been a pleasure exploring these elements with you.
The pleasure was all mine. And remember, everyone, there's always more to learn, always more to discover about the elements and the world around us.
That's the beauty of science. It's a never-ending journey of exploration.
So keep those minds curious and keep exploring. Thanks for joining us on this deep dive into the D and F block elements. We'll catch you next time for another exciting adventure in chemistry.